Good afternoon, everyone, and welcome to the second edition of Pinfa Sparks. I'm Esther Ajaman Budu, Pinfa Sector Group Manager, and I will be moderating today together with Pinfa Chair Thomas Futaha. Today's session is Closing the Loop, Recycling Strategies for Flame Retardant Additives, looking at how recycling strategies can evolve whilst maintaining essential functionality, including fire safety performance. Before we start, a brief compliance reminder. This is a Pinfa Suffolk hosted meeting, so we will keep the discussion strictly to the agenda and in line with competition law. You can see our Suffolk do's and don'ts displayed on your screen. Thank you all for your compliance. Also, we will like to mention that Suffolk does not authorize meetings participants to use any audio, video, transcription, or AI tools to record or transcribe meetings organized under its umbrella. Please check your settings now and disable any assistance that could access the meeting. Thank you all. Next, I will share a few housekeeping points. Please keep your microphones and cameras off during the duration of the webinar. Questions will be in writing only via the chat function. Please note that the chat is visible to all participants. Finally, this event will be recorded, and recording will be shared on Pinfa's website and related communication channels. In terms of timing, we will start with a short introduction, then our speaker for about 25 minutes, followed by Q&A via chat. And we'll close at 14:45 Central Time. And with that, I'll hand over to Thomas Futaha, Pinfa Chairman, for a brief Pinfa perspective and to introduce today's speaker. Over to you, Thomas. Thank you.
Thank you very much, Esther. Also welcome to you all for our today's webinar. In our series of webinars, the second one about polymer recycling and closing the loop. And a quick introduction to Pinfa. Pinfa is the Phosphorus Inorganic and Nitrogen Flame Retardant Association, and it represents 26 members, including manufacturers and users of 3 major technologies of non-halogenated flame retardants, which are phosphorus-based flame retardants, nitrogen-based flame retardants, and inorganic flame retardants. We have also sister associations like Pinfa North America and Pinfa China. Next slide, please. Yeah, so why flame retardants? Flame retardants reduce flammability and slowing down ignition. They are interfering with the burning process and they lead to a limiting heat release and flame spread. So flame retardants are essential for fire safety. And fire safety is an essential part of our modern society as we are surrounded with various materials, surrounded with electricity, digitalization, and so fire resistance and fire safety is an essential part of our today's life. Next slide, please. So with flame retardants, there is much more time in the case of fire for escape. There's more time to save lives and goods. And so there's more information about the mode of action of flame retardants can be found on our website. Next slide, please. And here we have the Pinfa members. We are very proud to have around 30 members, also downstream members. And if you're interested to join Pinfa, please feel welcome to give us a note. Yeah, and you see happy faces with some great colleagues of mine who are present today. At least most of those colleagues are here. That's the Pinfa Europe team. And Pinfa, of course, has a shared vision of continuously improving the environmental and health profile of flame retardant, of our flame retardant products, which help to maintain and to produce fire safety, especially to have sustainable fire safety. And our commitment is also to maintain high fire safety standards across the world. Next slide, please. And yeah, for more information, please check out our webpage and follow us on LinkedIn. And now we come to our speaker. I'm very happy and very proud to present Nacho, who is based in Valencia. Valencia is not only known for oranges, for beaches, but also for a great city, for great architecture, and for AIMPLAS, which is a leading technology center in plastic innovation, sustainability, and as well in chemical recycling technologies. And Nacho is a researcher there. He specialized in the valorization of complex plastic waste and advanced recycling processes. So Nacho, we are very excited to have you here today. So please, the stage is yours, and thank you very much again for being here.
Okay, thank you very much, Thomas, for the good presentation, and thank you also, Esther, for and all the Pinfas people that are around here. Well, as Thomas says, I'm Nacho. I work in the chemical recycling of AIMPLAS, and today we are going to see how we could close the loop regarding the recycling strategies for flame retardant additives. Sorry, I don't have the control now. One moment. I need the control.
Did you?
I'm waiting for the approval to take the control.
Okay, 1 second.
Okay. No, okay.
You got it? Great.
Yeah, thank you. Thank you, Esther. Okay, so we are going to start this presentation. First of all, as Thomas says, we are AIMPLAS. We are a technological center located here in Valencia with more than 35 years of experience in the plastic sector. And well, as you know, plastic sector is around us in everything. We start with, we work in the entire value chain of the plastics, starting from the polymer synthesis, obtaining these raw materials. We make the compound, all the processing manufacturers, blowing, extrusions. And we work also together with the end user companies to give them this knowledge and also obviously in this part of recovery of plastic waste and how we can make this improvement in the circular economy. For that, we work in the R&D sector, providing this knowledge to the companies and to the different entities. We work also making technological services, and always we are open to make these webinars, workshops, or also training sessions to different companies. So this is to put into context about AIMPLAS. But what we are going to see first is about the context, why we think and we know that the flame retardant additives needs to be recovered or needs to be cleaned from the polymer matrix. We will see it later. We will see a little sum up of the different recycling technologies, and we will see a final strategies with some examples that we could use for these recycling technologies. So, closing the loop, as you know, we have different phases. The first is this collection and sorting, very important. Later, we need to apply these recycling technologies to the flow that we recover and we sort in different flows. And once we make these technologies, we obtain some additive or some polymer that we need to purify or we need to use to reintegrate in these new materials. But as you know, we start with some plastic waste that is becoming increasingly is very complex because we have multi-material, we have a lot of different kind of additives. Obviously, the contamination during the life of the plastic, and that is why we also need to have the perspective of the separation process, sorting process to obtain some flow as much as homogenized and equal in the time as possible. And why we need to recover this kind of additives? Well, these are essential for the performance nowadays, as Thomas says, fire safety, performance, durability, depending on the additive. In that case, the flame retardant, as you know, is very important to make more safe the life during in the construction sector, cloth sector, and all different sectors. And the current technologies, they are still missing this part of recovering some additives with high functionality, and we are here now to see how we can make it more safe, effective, as circular this loop, seeing how we can separate or how we can recover the different additives with higher functionalities to improve this reduction of waste, conserve resources, maintain safety and performance, and enable a circular future. So, as I said, we have inside the materials a lot of different polymers, but also a lot of different additives, also fillers, stabilizers, flame retardants, and the weight could go up to 30% in weight, and in some kind of applications could be higher. So that is why this heterogeneous waste is what we need to think when in the real waste, not only in the virgin waste that is more easy to recover and reintroduce. So the current recycling technology lose this functionality. The mechanical recycling, basically, we wash, we shred, and we melt to obtain new pellets. And what happens in these new pellets? The additives that are in the waste remains in the final polymer that we obtain. Only to know how the global consumption of flame retardants is more than 2.5 million tons per year. All of different flame retardants, I put here halogenated, but also the most sustainable, like phosphorus base, also nitrogen base, and inorganic ones that and we need to know that it's not a homogeneous additives in all of these applications. And when we cannot have any recycling route to recover it or to clean it for the new product, we are losing this functionality and high chemical value with loss of the flame retardancy of the product, loss of material certification. Obviously, the legacy is very important, but also this loss of the economic value. So, to repeat, we need to recover, preserve, and reintegrate these functional additives to improve all of these critical parameters. So, why, as I said, we could recover this grinding, melting, reprocessing, and we cannot selective separate. We dilute because normally we put some recycling content with different percentage, and that what we obtain is a new pellet with less flame retardant quantity of additives. Also could happen that there is halogenated flame retardant could not obtain the legacy requirements, because in the future the normal is that these halogens we cannot use them. So another possibility, thermal degradation during the reprocessing parameters, well, could happen that the own additive goes the composite. If it is flame and halogenated, is worse, because obviously this chloric acid or bromic acid is bad. That's why the impact final is loss of flame retardant performance, release of corrosive and hazardous gases, and this loss of value and regularity compliance. And the last critical thing is this polymer degradation and an additive that remains this final material incompatibility, and the result is that the material no longer meets the performance and requirements and safety standards, the standards that we need. That's why the conventional recycling, as we see, is not designed for this additive circularity. Normally, it's more focused in the polymer matrix than the additives. So, as I was repeating, the regulatory barriers are critical also to restrictions about REACH, Stockholm Convention. So it's not only regarding the technical parts, also the legacy that we need to obtain. So as final conclusion regarding the context, this mechanical recycling is not enabled to circularity, leads to downcycling normally, and only preserves the material. The polymer backbone may be retained, but normally the functionality of the high additives like flame retardants is lost. So we need to focus in this, and we are going to see how we could improve this part in the next part of the presentation. We will see it, but basically we could make this selective separation by dissolution, chemical recovery using some solvolysis, for example, and we are going to focus mainly in these two first technologies like dissolution and solvolysis, and also we will see one more about pyrolysis that could work, but well, we will see. So this is the context. Now I want to make a little sum up about recycling technologies that exist. As you know, mechanical recycling is the more traditional, but another one is the dissolution. Is very normally it's called physical process, and basically here is touched one material. Normally is the polymer, but could be some additive or some part that is the recycling is to dissolve selectively the polymer or the additive. When we cannot make this dissolution selectively, what we can make is some solvolysis or enzymolysis chemical process to break the polymer chain to obtain the monomer. Another additives could remain in the dissolution, and we could recover by another techniques. Another kind of recycling technology that we are not going to focus would be the pyrolysis or gasification to obtain some energy, and this is not the scope of this webinar. So to sum up, we could break the polymers or the materials with temperature, solvents, or enzymes as sum up. And with the physical recycling, dissolving, we don't not break the polymer. We only dissolve selectively the polymer or the additive that we want. And with that, what we could make is this extraction of additive of interest, eliminate of inherited substances, or even separate the different polymers or materials by different layers. Okay, one first example, for example, we have the polyethylene with a 30% of flame retardant bioadditive, and we make the dissolution of the polyethylene. After the filtration process, you could see like in the filter, we recover the biofilm retardant, and the polyethylene, after the dissolutions, we need to make the reprecipitation process to make this precipitation of the polymer. And after filtration, at the final of the process, we obtain the polyethylene from one side and the biofilm retardant from another side in that case. The next process, you could make this pellet, a new pellet of polyethylene with or without biofilm retardant, and you can use the biofilm retardant for the same purpose or for another kind of polymer or application. Only other examples for the ink process also could be interesting in the textile market, but also for polymer separations. One example is the artificial turf made by different polymers, and after selectively dissolution of one polymer or another, we could separate the different ones after this cascade process, targeting first one polymer and later another, and the different filtration process between them. And the last one about as example is the lamination process. Basically, here what we are going to dissolve is the glue between the layers, and after the dissolution of this, we will recover the different layers. By the typical mechanical recycling, we could sort the different materials in different layers to make this mechanical recycling. Another example is for example, the pyrolysis, only to put into context what we are talking about. In this case, the example is wind blade residues. And after the thermal cracking by pyrolysis, we recover different fractions. In the solid one, we have the char, in that case with fibers, but we need to think that if we have a polymer with inorganic additives, the inorganic additives could remain in this solid, in this char. So we will see it later, but could be one of the strategies to recover some additives, flame retardant additives that are inorganic, because obviously if they are organic, they are going to be decomposed and we will obtain in the pyrolytic liquids and other substances. And also we recover the gas during the pyrolysis. The another one is the solvolysis, that is we could use it also for some kind of polymers like polyamides, polyethylene terephthalate, or and others. And with that, the same. Normally, we recover, in that case, the example is with wind blade residue. So we obtain in the solid part the fibers, but the same. What we attack is only the polymer, and if the additive remains in the dissolution as a solid, because we don't make any change in the chemical structure of the additive, after the filtration, we could recover the reaction crude from one side. From here, we could recover some monomers or oligomers or some substances of interest. And in the another part, we could recover the additive that remains solid in the crude. And after these filtrations, we could recover flame retardant or an additive. In that case, the example is a fibers, but we need to think that we could use it for another kind of materials. Okay, now we are going to see the final part. This is like a sum up of the different strategies that I said, focusing in that obviously the reality is that it's not one recycling route for flame retardants. There is not nowadays any industrial process, because normally the current technologies are focused more in the polymer matrix, how we could recover the polyethylene or the polypropylene or PET or whatever, and not in the additive centric. It's true that we talk about solvolysis or chemical strategies. It's more easy to focus on the another materials than when we talk about mechanical recycling. Here we could see that there are different kinds of flame retardants, phosphorus-based, nitrogen-based, inorganic ones, that depending on the process, we will focus in ones or others. So, key paradigm shift, what I want to say here is that the process driven needs to be from the chemistry driven. The conventional approach, we apply these recycling technologies for the waste. Normally there are thermoplastic waste and we obtain a pellet. But if we want to go one step more, we need to think about, okay, in that system, which kind of polymers we have, if we could have which kind of additives we have better. That is sometimes more difficult, but we need to try to make this analysis part to make the strategy more selective. And finally, what we need to make is understand the system, select the strategy focusing in what we want, apply this strategy to the waste, and recover the value targeting, in that case, in the additives or the polymers or both. The best option always is both, but we need to focus in what we want to recover. And we will see how we could focus in the flame retardants now with some examples. Because at the final of the process, with this kind, what we are going to make is preserve the performance, separating the different materials at the final of the process. So we need to be case specific, depending on the type of the waste, the heterogeneity or homogeneity that we have, and chemistry driven, thinking in what we have and what we want to obtain. This is needed to close the loop for flame retardants, because we must move from process centric to chemistry centric when we want to make this step more. So, first of all, polymer type. If we have polyolefins or polyester, polyamides, polyurethane, maybe a mix of them, but we need to know a percentage of them if it is possible, because this is going to determine thermal stability, solubility, processing windows, and basically the chemistry driven that we are going to have in the system. flame retardant type, if it is organic or inorganic. Very interesting to know which method we want to use, and if it is reactive or additive. Normally nowadays are more additives, but could happen that some flame retardants could be inserted in the same polymer chain that allow us to make another kind of separation, allowing for solvolysis to recover the monomer that has this flame retardant inherently in the monomer, because this is going to determine the separation feasibility and chemical stability of the flame retardant. And the last target of the process, here we are going to focus obviously in the recovered additive, but depending of the process, we could recover polymer or both. And normally the best option obviously is both, because if we obtain a process stabilized with good results for both, the will be better the value of the process. So it's no one-size-fits-all solution nowadays, and the chemistry-driven decisions must be done. So to finalize, some examples. For example, this is strategy 1 to dissolve the additive. Okay, we have a flame retardant containing some plastic waste. Normally, we need to know which kind of flame retardant we have, as much as possible to go more easy to the wood solvent one. If not, we need to start with more kind of test, obviously. Another thing is that there are a lot of different technologies that we could apply to this. For example, exists the supercritical fluids, that basically what one liquid, if we reach some pressure and temperature, this liquid, their behavior is like a gas and liquid, and this is normally, if we work in these conditions, the liquid and the solvent could go more easily through the different polymer chain and makes this flame retardant dissolution more easily. Or, for example, use microwave radiation to obtain the temperature. We have a lot of different techniques to apply to this kind of different strategies. So when we are going to, this is applicable normally when the flame retardant is organic, because if it is inorganic, we cannot dissolve them normally. And the solubility obviously needs to differ from the rest of the matrix, because if not, we will dissolve a lot of different impurities that we need to separate later. So the examples here, we have an organic flame retardant. We put some solvent with the pellets and the flame retardant, and after one pressure at temperature, the solvent solubilize this flame retardant. After the filtration, we will recover the polymer from one side and the flame retardant from another side. The most critical thing here is like the flame retardant is between the chains. So we need to think that the condition of pressure could be higher to improve this pass of the solvent through the chains. Another different thing that normally we use this is focus on the polymer. The same as the main matrix is polymers. Normally it's more easy to dissolve it because we do not have to make the solvent go through the polymers, because the polymer is going to be dissolved entirely. So here is similar, the strategy, but focusing now in the polymer. We need to see which polymer is. Normally with polyolefins, they are more easy to dissolve, like PET, for example, or depending on the polymer, but we will make some different tests focusing on the dissolution of the polymer, and after the filtration, we will recover the inorganic flame retardant, or if it is an organic, could be, but we need to be sure that the solvent is not going to dissolve also the flame retardant. So basically, we need to think as with the chemistry of the system. And I think, yeah, three more. There could be that the polymer is not feasible for dissolution, for example. So the PET could be very difficult to dissolve, or some kind of polymers that are very difficult to dissolve. And what we are going to make is break this polymer into monomers or oligomers. After the process, these monomers or oligomers could be dissolved, because now these monomers normally they are easily to dissolve. And the same, after break the polymer and obtain the monomers. After filtration, we will recover in the solid state these flame retardants. But the same, we cannot use some reagent that is going to attack the flame retardant, because we need to try to have the flame retardant in the same level as was during the pellet. So here the goal is to recover these high value monomers, and while we are retaining the flame retardants in solid state. The last, and normally we are not focusing in that, but could be a possibility, is the pyrolysis strategies. This only works, as I said before, for the inorganic ones. If we work in some temperatures that the flame retardant not have any degradation with this temperature, in the inorganic flame retardant will be remain in the char, and we need to make this extraction of the flame retardant in the char by the different techniques depending of the kind of the flame retardant that we recover. But it's true that normally we prefer the another three strategies that I present than this one. So here normally we will recover the oil and the gas that we could use for energy, or even chemicals of interest, because we could recover chemicals of interest in the pyrolysis. And in the solid one, we will recover the char enriched with this inorganic flame retardant. A sum up, what not to do, applying technologies without chemical understanding, because basically, obviously, pyrolysis with halogenated flame retardant also will be create a lot of bad components that are very dangerous. Also, pyrolysis without evaluating the stability of the additive, or dissolution without selectivity that we want. So basically, we need to think the system, what we want to obtain, what we want to achieve. And the result, when we don't do that, contamination, loss of value, a non-viable process at the end. And the case is basically, as you say, nowadays there is no universal solution exists for any for the high waste that exists, and we need to make this chemical characterization and make a tailored process design for the waste that we want to upcycle. So that's all. Thank you very much for your attention, and I will be there some minutes more for any question.
Thank you very much, Nacho, for this very informative presentation.